What is the specific problem addressed by the proposed method in the paper?
The specific problem addressed by the proposed method in the paper is the improvement of semantic alignment between input prompts and output audio in text-to-audio models. The paper focuses on enhancing the fidelity of text-to-audio models by fine-tuning them using a novel approach called direct preference optimization, DPO, with diffusion models. The key issue tackled is aligning the generated audio with human preferences effectively. This is achieved by creating a preference dataset called Audio Alpaca, which contains diverse audio descriptions with preferred and undesirable audios. The method aims to ensure that the preferred audios accurately reflect the textual descriptions, while the undesirable audios have flaws like missing concepts or incorrect temporal order. By training the model on this preference dataset using DPO diffusion loss, the paper aims to significantly improve the semantic alignment between input prompts and output audio, leading to superior audio generation quality compared to existing models like Tango and AUDIO-LDM2.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by first creating a preference dataset called Audio Alpaca for text-to-audio generation. This dataset is generated using various strategies such as multiple inferences from the same prompt, inferences from perturbed prompts, and inferences from temporally perturbed prompts. The audio samples are then paired with their corresponding text prompts based on clap matching scores. The winning audio samples, which are most aligned with the text prompts, are selected along with the losing audio samples. These pairs form the preference data points in the dataset. The selection process ensures that the winning audio is strongly aligned with the text prompt and has a higher clap score compared to the losing audio. The dataset is further filtered based on clap scores from two different models to ensure robustness. The DPO, direct preference optimization algorithm, is then applied to fine-tune the text-to-audio model, Tango, on the Audio Alpaca dataset. During fine-tuning, the model learns from both desirable, winner, and undesirable, loser outputs, improving the semantic alignment between the input prompt and the generated audio. The DPO objective optimizes the model to generate audio samples preferred by human perception by penalizing undesirable outputs and promoting preferred outputs. This approach allows the model, Tango 2, to better map the semantics of the input prompt into the audio space, resulting in improved audio quality and relevance to the text input.
What are the theoretical or practical benefits of using the DPO diffusion approach in the text-to-audio model?
The theoretical and practical benefits of using the DPO diffusion approach in the text-to-audio model lie in its ability to align the generated audio outputs with human preferences effectively. The DPO diffusion approach allows the model to learn from both desirable, winner, and undesirable, loser audio outputs, which is crucial in improving the semantic alignment between the input prompt and the generated audio. This approach enhances the overall audio quality and relevance to the text input by penalizing undesirable outputs with missing concepts or incorrect temporal orderings, while promoting preferred outputs with correct event sequences. The DPO diffusion loss function optimizes the model to generate audio samples that closely match the input prompts while maintaining a balance between desirable and undesirable outputs. This methodology ensures that the generated audio reflects the intended content of the text prompt accurately, leading to superior performance in both objective metrics like FAD, KL divergence, IS, and clap score, as well as subjective evaluations of overall audio quality and relevance. Additionally, the DPO diffusion approach provides a more robust and practical alternative to reinforcement learning with human feedback, RLHF, by leveraging the same BT preference model, but incorporating undesirable outputs in the training process, thereby enhancing the model's ability to generate high-quality audio outputs aligned with human preferences.
How is the preference dataset Audio Alpaca created and pruned for DPO fine-tuning.
The preference dataset Audio Alpaca is created by first generating diverse audio samples from various text prompts using the pre-trained Tango model through 3 different strategies. Strategy 1 involves selecting diverse captions, clustering them, and generating multiple audio samples with different denoising steps. Strategy 2 perturbs the captions using GPT-4 to create semantically close variations, then generates audio samples. Strategy 3 focuses on prompts describing sequential events, creating temporal perturbations and corresponding audio samples. These strategies result in paired text prompts and audio samples. The dataset is then pruned for DPO fine-tuning by computing clap matching scores between text prompts and audio samples. The audio sample with the highest matching score is considered the winner, while the others are losers. The winning audio must have a minimum clap score with the text prompt. The losing audio must have a minimum clap score, and the winning audio must have a higher clap score than the losing audio. An ensemble filtering strategy based on 2 clap models is used to ensure the selection process is robust. The final preference dataset Audio Alpaca contains 15,025 samples that meet these criteria, ensuring alignment between text prompts and audio samples while maintaining a balance between preferred and undesirable outputs for effective DPO fine-tuning.
What were the main results achieved with the Tango 2 model in comparison to Tango and AUDIOLDM2, based on both objective and subjective evaluations?
The main results achieved with the Tango 2 model in comparison to Tango and AUDIOLDM2, based on both objective and subjective evaluations, are as follows. Objective evaluations. 1. Tango 2 significantly outperformed Tango and AUDIOLDM2 in terms of objective metrics. Tango 2 achieved scores of 2.69 for FAD, 1. 12 for KL, 9.09 for IS, and 0.57 for CLAP, 2. Tango 2 showed improvements in audio quality, diversity, and semantic alignment with the input prompt compared to Tango and AUDIOLDM2. 3. Notably, Tango 2 demonstrated enhanced audio quality in KL and as metrics, surpassing various versions of AUDIOLDM and AUDIOLDM2. 4. There was a substantial enhancement in the CLAP score for Tango 2, indicating superior semantic alignment between the textual prompt and the generated audio. Subjective evaluations. 1. In subjective evaluations, Tango 2 received high ratings of 3.99 in overall audio quality, OVL, and 4.07 in relevance to the text input, REL. 2. Tango 2 surpassed both Tango and AUDIOLDM2 in subjective assessments, indicating significant benefits from preference modeling on the Audio Alpaca dataset. 3. The subjective findings diverged from a previous study where Tango fine-tuned on music data showed lower audio quality, highlighting the effectiveness of preference modeling in enhancing audio quality and relevance to input prompts. 4. AUDIOLDM2 performed the worst in subjective evaluations, with significantly lower scores in both overall quality and relevance compared to Tango and Tango 2. Overall, Tango 2 excelled in both objective and subjective evaluations, showcasing superior performance in audio quality, diversity, and semantic alignment with input prompts compared to Tango and AUDIOLDM2.
What are the implications of the temporal and multi-concept prompts analysis results on the performance of Tango 2 and AUDIOLDM2 models?
The temporal and multi-concept prompts analysis results have significant implications on the performance of Tango 2 and AUDIOLDM2 models. Tango 2 outperforms AUDIOLDM2 in both objective and subjective metrics when handling prompts with multiple sequential events and those without temporal sequences. This indicates that Tango 2 is more adept at capturing the nuances of prompts with temporal dependencies, showcasing its ability to generate audio outputs that align well with the input descriptions. Additionally, Tango 2 excels in scenarios where prompts involve multiple concepts, such as simultaneous actions, compared to AUDIOLDM2. This suggests that Tango 2 is better equipped to handle complex prompts with diverse elements, resulting in superior audio generation quality and relevance to the input prompts. The success of Tango 2 in these analyses can be attributed to the DPO training approach, which emphasizes the differences between generating preferred and undesirable audio outputs, penalizing incorrect temporal orderings, or missing concepts in undesirable outputs, while promoting correct event sequences and concept presence in preferred outputs. Overall, the results highlight the effectiveness of DPO fine-tuning on the preference dataset Audio Alpaca in enhancing the performance of Tango 2, especially in handling prompts with temporal and multi-concept complexities, showcasing its robustness and adaptability in text-to-audio generation tasks.